We are going to use the binomial theorem to help us multiply or expand binomials. So remember, binomials means that we have two terms. So we could have a plus b to the 0 power. Well, we know anything to the 0 power is just 1. So to show the pattern a little more, we're going to write it 1 times a to the 0, b to the 0. Then we have a plus b to the first. Well, that means we have 1 a to the first. That's a b to the 0, plus 1 a to the 0, b to the first. That would obviously simplify to a plus b, but again, we have a pattern that we're trying to show. A plus b squared, that means we need to FOIL it. So you could write a plus b times a plus b and then actually multiply those through. Well, we would be given a squared, b to the 0, plus 2ab plus a to the 0, b squared. A plus b cubed has a pattern as well. We would have a cubed b to the 0, plus 3a squared b to the first, plus 3a to the first b squared, plus a to the 0 b cubed. So our pattern that's showing here, notice we have our coefficients. We're going to talk about those in a minute. But as far as our variable goes, we have an a to the first, which correlates to our power. B to the first correlates to our power. Here we start with a squared. Our middle term has one of each. Our last term, the b has 2. Okay, so our first variable is decreasing powers each time. A cubed, a squared, a to the first, a to the 0. Our second variable is increasing. B to the first, b to the first, or excuse me, b to the 0, b to the first, b squared, b cubed. But before we talk any more about the variables, let's see where these coefficients come from, the numbers. Our coefficients come from Pascal's triangle. That's just Pascal is a person and he came up with this pattern. It forms the shape of a triangle. So anything to the 0 power is 1. And then if we're expanding something to the first power, both terms have 1s as their coefficients. Anything to the second power, the pattern goes 1, 2, 1. If you look up here, 1, 2, 1. Third power is 1, 3, 3, 1, which fits with that pattern right there. The fourth is 1, 4, 6, 4, 1. And then the fifth is 1, 5, 10, 10, 5, 1. This goes on forever and ever and ever. Up until the fifth power is generally what we use. Okay. Another way to figure out Pascal's triangle, if you can't memorize that pattern, you can find it using combinations, which we talked about the other day. A plus b to the 0 is 0, choose 0. To the first is 1, choose 0, and then 1, choose 1. Anything to the second would be 2, choose 0, 2, choose 1, 2, choose 2. To the third, 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. So hopefully you see that pattern. That can go as long as you would like to make it. That leads us into this binomial theorem. This looks like a lot and it's messy. I promise it will make sense. These n choose whatever in parentheses are just those Pascal's triangle coefficients. So you won't have to do this each time. You can just use the coefficients from Pascal's triangle. And then the variables follow that pattern that we talked about. Remember, our first variable always starts with the power that our binomial was raised to. Our second variable always starts with a 0 power. Then our first variable, in this case a, decreases a power each time. So n to n minus 1, to n minus 2, to n minus 3, and so forth. Eventually that a would get down to a 1 power and then to a 0 power. Likewise, our second variable increases power. So b to the 0, b to the first, b to the second, b cubed, b to the fourth, b to the fifth, so on. Eventually we would get up to b to the n power. So we're going to try to make that make a little more sense. So we're going to take x plus y to the 5th power. We're going to follow this pattern. Okay, it would be 5, choose 0, x to the 5th power, y to the 0. Plus 5, choose 1, x to the 4th, y to the 1st. X decreases a power, y increases a power. Plus 5, choose 2, x cubed, y squared. 5, choose 3, x squared, y cubed. Remember, our x's are decreasing, y's are increasing. Plus 5, choose 4, x to the 1st, y to the 4th. 5, choose 5, x to the 0, y to the 5th. Okay, knowing that to the 5th power we can use Pascal's triangle, if you wrote that down, you know that this coefficient would be a 1, 5, 10, 10, 5, 1. I rewrote it and simplified it. It simplifies here. So all those things, those combinations in parentheses are just coefficients. Let's try a little more complicated one. If we have 2r minus s cubed, our coefficients would be the third row, or our cubed row of Pascal's triangle. So our coefficients are 1, 3, 3, and 1. Knowing that, I know I'm going to have 1 times, this time our a value is 2r, and our b value is this negative s. Can't really see that negative, but it is in there. Negative s to the 0. Plus 3 times 2r squared, negative s to the first, plus 3 times 2r cubed times negative s squared, plus 1 times 2r to the 0 times negative s cubed. When you go to actually simplify this, because we can't leave our final answer like this, we have to actually cube everything. So you have to cube the 2 and the r. So that becomes 1 times 8r cubed. Anything to the 0 is 1. 3, square the 2 and the r to get 4r squared. S to the first, that should be a negative. I missed that in there. That should be a negative s. And then 3, 2r to the first. I might have said cubed earlier. My apologies. That should be to the first power. So that's just 3 times 2r times s squared. And then that again should be a minus s cubed. One last simplification, we get 8r cubed, and multiply your numbers here, minus a 12r squared s. I just brought that minus out in front, plus a 6r s squared, and then I brought that minus out in front again to get a minus s cubed. Okay, sometimes we'll be asked to find one term out of that giant binomial expansion. So if you're asked to find a particular term, say we're looking for the fifth term of p plus q to the 10th power. We have this little formula. I just plugged the 10 in because we're looking at something to the 10th. If it was to the 5th, those would just become 5s. When we go to find the fifth term, our r value is then 4. So we would have 10 choose 4 times p to the 10 minus 4 q to the 4th. That simplifies. 10 choose 4 is 210, p to the 6 q to the 4th. That just saves you a lot of time. You don't have to actually expand the entire thing if they're just wanting one term. So it's a shortcut. Okay, we have a binomial experiment. Binomial, if you remember, bi means 2. So we have an experiment that has exactly 2 outcomes every single time. So we use the letter P to signify a success, and then a Q for a failure. And we can then find probabilities of these binomial experiments. So we're going to have n successes, but m total trials. So our formula for our binomial probability would be m trials, choose n of them, so n successes. P in this case, I think I put it down here, is the probability of our success, and Q is the probability of our failure. Okay, we wanted n successes, so our probability of success is raised to that n power, and our probability of failure is raised to the m minus n, because we have m total minus our n successes would give us our failures. Let's do an example. We toss a coin 4 different times, and we want to figure out the probability that we flip exactly 2 tails. Well, in our case, we have our m value is 4, our n is 2, our p is the probability of a success, which is a tail, and q would be the probability of a failure, which would be a head. So we have 4 choose 2, 4 trials, we're choosing 2 successes. Probability of flipping a tail would be half, right? Heads or tails, so 50%. So half, we want 2 successes. Probability of flipping a heads is also a half, raised to the 4 minus 2 power. 4 choose 2 gives us 6. Half squared is a fourth. This becomes a half squared again, which is another fourth. We get 6 over 16 if we multiply, which is 3/8. Okay, one more quick example. Probability of at least 2 tails. We could take the probability of 2 plus 3 plus 4, or we could take 1 minus the probability of 0 minus the probability of 1. Okay, here is your work. We're about out of time, so look through that work and work through it on your own as well.